Okay, so today is part 2 of unit 1. Okay, so I'm still, just as a formality, I'm still going to take you to the introduction and the learning outcomes, especially for those who are joining us for the first time today. So an operating system facilitates the interaction between hardware resources and the computer and the user of a computer. The purpose of operating system is to make the computer system convenient to the users. The operating system is responsible for controlling the computer devices. It is very important to know the relationship between hardware resources and operating system, okay? So in actual fact, this whole module is based around computer architecture. And the operating system, remember, is at the center of that because the operating system controls hardware. It controls how the hardware operates. Okay, so our focus, that's why the module is called system software. Another term for system software is operating systems. So we cover the following learning outcomes. Describe computer architecture and organization with emphasis on topics that relate to operating system design. Demonstrate an understanding of operating system design. Explain the process of how instructions are executed with regard to processor and instruction registers, interrupt, and scheduling. Describe the various input-output communication techniques. So those are the learning outcomes that we're covering for this lecture. Okay, so we touched on operating systems on Monday. Okay, so operating systems make it more convenient for us to use computers. Before operating systems existed, we had to type things in commands. Okay, so you needed to be very techno savvy for you to be able to use a computer because literally you had a book, okay, a book with multiple commands. How do you move from one directory to the other? You had to type a command to do that, which is still being used today by people who prefer Linux and so forth. They're still doing things command based. There is still also on Windows computer the command utility. So the command utility was the one that was used before. In actual fact, you can control your old computer using the command utility because that's how olden day computers actually worked. So they put that layer of operating system there to provide a more graphical interface for the computer. And you can see that I included in today's lecture, I included additional pictures for you to understand these concepts. Monday's lecture was more of a text-based thing. So you see these are some of the examples of operating systems that we are aware of. There's mobile operating systems, and then there's also desktop operating systems. So we have the Mac OS, we have Android, we have Apple iOS, Windows XP, we have can somebody please mute their mic because I can hear feedback from it. Okay, so there's Windows 10. Okay, so the most popular one, and we can all agree, is that it's Windows. It brings an aspect of a bit of affordability, but also convenience. If you go to Linux, you must be very technical to use Linux, okay? It's a very complex operating system to use as a regular end user. So we have Windows, which is the most popular one. And then you also have Apple. Apple, the problem about it is that it's very expensive, okay? And it can also be very confusing for people that are not used to it. So we also discussed the basic elements of a computer. Look, a computer is made up of several components, but it's key for us to recognize the key ones, which means you can't even call this box on the right-hand side a computer if it doesn't have those components. Okay, you can't even call it a computer. Okay, so we have the CPU, and the CPU is in charge of executing instructions. We will cover it more in detail in the slides that follow. We have the system bus, okay, which is like the pathway which the data travels between the different components. We have the main memory, which Monday we said the main memory is like an Excel spreadsheet for the CPU. The CPU sort of stores everything that it has to do within the main memory, or sometimes we refer to it as RAM. Okay, so what kind of content is stored in this RAM or main memory? It's instructions, it's data, it's programs waiting to be executed. Okay, those are the most popular content that's stored in main memory or in RAM. Then we also have our input-output modules, okay? And also that we'll cover in the slides that follow. So you can see this picture here, and it's labeled, it's showing you the different slots. So this is where the RAM would go, okay? Our main memory would be somewhere over here. And then here would have somewhere our CPU with sort of a heat sink, a cooling system. You see, when normally you see a fan, it has to be cool because it overheats, okay? It overheats, it's always busy, it's always executing instructions. So you need some sort of cooling system. And we also have our expansion slot, our actual motherboard, which houses all of these components, our power supply. So it doesn't matter, you can have all of these. You see, this is a very basic computer. You can even have a hard drive, but if you don't have the CPU there, you don't have any RAM, you can't call it a computer at all. That's why we say it's the basic element. So there's the CPU, and there's an example of how it looks like, okay, in real life. It's a chip. This is how it looks at the back, and this is how it looks in the front. Okay, so this is the conceptual diagram, which sort of explains how everything operates. We have input, okay? We have input, we have process, we have output. Our input comes through input devices, which are keyboards, mouses, and so forth. You know, you've covered that in IS before. So the whole concept of process is placed upon the CPU. It's the responsibility of the CPU. And I'm saying to you guys, the CPU executes data, executes instructions, executes programs, okay? And then you have RAM, we have our hard drive, and we have our CDs, which these are secondary memory we discussed on Monday. Secondary memory, primary memory. This block represents a grouping of components: CPU, RAM, hard drive, compact disk. All of these are separate components, okay? But they all form part of that whole process of processing. And then we also have output. And when things are displayed as output, obviously the end result, the monitor you're sitting in front of now, you're watching, is output. The printer is output. Speakers, if you're playing a song, that's output, okay? So that's a typical flow of the CPU in terms of input, process, and output. And the CPU has its own components, which we said it's the ALU, okay, within the CPU itself. And this particular component is in charge of actually performing the calculations. This is the actual component of the CPU, which does comparisons, addition, subtraction, and so forth. The control unit, okay, is in charge of directing instructions into the correct place, okay? So when things come from the RAM into the CPU, the control unit is the one that decides which part of the register does it actually go to, okay? And we will cover the different classes also of registers, and you'll see the significance of the control unit in later on in the presentation. Again, you can see in front of you, main memory, also referred to as RAM. And number 1 would be an example of, number 1 and 3 would be an example of a RAM chip that you would find on a laptop computer, okay? And also 2 and 4 is the one you're most likely to see. You can see they're longer, so most likely you'll see those on a desktop. Why do we call it main memory? Or why do we call it primary memory sometimes? The main reason is because when it comes to computers, memory is seen as something that is temporary, okay? We say it's volatile because once the computer switches off, the RAM is wiped completely, okay? Everything that was stored in there is wiped completely, okay? So we refer to it as main memory because the computer uses it as a primary source of storage, meaning the CPU. The CPU does not use your hard drive. It uses RAM. Although we can acknowledge that the hard drive is a form of storage, okay? So that's the reason why it's called primary and main memory, okay? So once the RAM is overwhelmed, because they do come in sizes, and if you go to buy one from the shop, you're going to notice that here it's labeled that it's 2 gig, it's 4 gig, and computers normally have more than one RAM slot, so you can have 2 gigabyte RAM chips within your computer and so forth. You can combine these, but they have to be at the same speed. They have to be operating at the same speed. Otherwise, you won't get the end result, okay? So main memory, primary memory, that's why it's called main memory and primary memory, because the CPU uses it as a first instance, okay? And then we have storage devices that are secondary memory because they are actually second instance, okay? So the CPU still uses them, but only uses them when it's under pressure, okay? And Monday, I even said to you guys, I made an example of people that are gamers that play a lot of games. Why do you think the game says we need you to have 6 gigabytes of RAM in order to play this game? Because when you take that game, when you download it or you put the disk inside the PC, that entire content is downloaded onto the RAM. The RAM is also shared by other programs and data on the computer in the background. So if the game is 6 gigabytes and you have 6 gigabytes of RAM exactly, you're going to see that you're going to experience some sort of issues. And hence they tell you we have minimum requirements and we have recommended requirements. So they will always recommend that that which is higher than what is recommended. Okay, sorry, than what is minimum. So what we tend to see now is that we have our flash drives, our floppy disks, very ancient technology, the floppy disk. We have the hard drive. We have these tape-based disks. We have the CD-ROM. All of these are secondary. Even if you have your flash drive plugged in there and your computer is running out of RAM, then your computer can use that flash drive as some sort of it can borrow from that flash drive, okay? So the whole process of borrowing is also time consuming. So therefore you end up experiencing lags, okay? You end up experiencing lags and delays in between. So that's why your computer tends to stutter when it's running out of memory, okay? So moving on to the next concept, which is the system bus. Okay, so we have the system bus, and in the earlier slide, I said the system bus is basically the pathway at which the data travels between the different components. And this is another screenshot of how a motherboard would look like. And you can see the CPU slot, and then this is where the RAM chips will go. So how does the data travel then between where the CPU is to where the RAM slots are? It has to use the bus, okay? And you can see these white lines that are on the motherboard. Some of them you can't actually see these lines, but the ones that are white, mostly they form part of what we call the address bus, okay? And addresses and data are sent, it's like the pathway at which this data and addresses or instructions travel between the various components of the computer. So moving on to the next concept, which is a microprocessor. So when you talk about a microprocessor, processors have existed for a very long time, for as long as computers existed. But thanks to microprocessors, our technology has become smaller and a bit faster. Okay, that's why now we have smartphones. And by the way, your smartphone is a computer because it does have memory, primary memory, and also has a CPU. Okay, so thanks to microprocessors, our technology has become smaller. Normal processors that existed back in the day were very big, but also they were less efficient. Okay, so now the things have become smaller and more advanced thanks to the microprocessor. Introducing this concept of multi-core processing. Okay, so we have a multi-processor computer, and then we have a multi-core processor. Don't confuse the two concepts. Okay, so we're talking about the multi-core processor. We say it is a processor, a single chip, like you saw in the previous slides. It's a single chip, but it's able to operate like it was two separate processors. And you can see here in the diagram, okay, processor 0. It has 2 cores. We can refer to it as a dual-core processor. Okay, core 0 and core 1, which means for this multi-core processor chip, it can execute multiple instructions at the same time, as if you had 2 separate single core processors in your computer. So that's the beauty of it now. We have all of these processors that are actually multi-core. And you may have seen i7, i5, i3, and so forth. That's what it means. It's the number of cores in there. So moving on to multi-processor computers now. So some computers have the ability, especially those computers that are used as servers, they have the ability to house more than one CPU. Okay, so we have CPU 1, CPU 2, CPU 3, for example. I'm just going to move on to the next slide so you can see this. Okay, so we refer to it as a symmetric multi-processor organization, separate physical CPU chips within the computer. Obviously, this solution is more expensive and it's definitely going to be faster than the multi-core, because you can imagine if comparing a computer that has one i5 processor inside compared to a computer that has 3 i5 CPU chips. Okay, it's definitely going to be more faster, definitely going to be more expensive. What are the advantages of using a? Yes. Anybody has a question?
Yeah, on the previous slide.
Yes.
I wanted to ask, what does L2 mean? Or
L2. Okay, we're gonna get to
L2.
that. That's the catch. Yeah, it's part of our lesson in the later slides. Yeah, sorry about that. So we've touched on main memory, we've touched on the system bus, and we touched on the input-output requests on Monday's lecture. The L2 is a type of catch, and we're going to discuss it as a separate topic later on. Okay, for now, I just wanted you guys to focus on the concept of it being a multi-processor computer system as in separate physical chips. Okay, I don't know why the teams didn't actually show your hand that you guys, because it normally shows here next to the name, but it's fine if you see that I can't recognize your reaction, then you can unmute yourself and ask the question. So what are the advantages of implementing systematic multi-processing in terms of performance? A system with multiple processors will yield greater performance if work can be done in parallel. Okay, yes, as well, multi-core does work in parallel, but for the fact that we have multiple physical chips, it means it provides greater performance. Okay, so it can do this parallel execution of instructions to a greater extent than that of a single processor with multiple cores. And in terms of scaling, vendors can offer a range of products with different price and performance characteristics. Okay, availability. The failure of a single processor does not halt the machine. And that's a very good point that they're raising here. So in the multi-core setup, because if it's one physical chip, if that physical chip heats up, then we don't have a processor anymore because the cores are integrated into the one physical chip. But in a multi-processor computer setup, we have separate physical chips, and if one overheats, then it does not affect the other ones. There's still some sort of contingency. So there's always a processor going to be available as a backup. And incremental growth, additional power processor can be added to enhance performance. So usually a computer that supports multi-processor setup would only come with one processor and then would have multiple slots. So it's up to you. If you want to increment your growth, then you go and purchase additional processors to enhance your performance. So moving on to the next concept, which is how a CPU actually executes these instructions. And in Monday's lecture, we said it happens in 2 stages, which is further divided into 4 phases. Okay, so 2 main stages. It's the fetch stage. Fetch it from where? Fetch it from the RAM or the memory. We have the execute, which is actually execute the program. Okay, so the processor fetches the instruction from memory. The program counter holds address of instruction to be fetched next, and the program counter is incremented after each fetch. So here they're making a specific example if the processor was executing a program. If we have a 32 based processor, it means it can execute 4 of these programs at the same time. Okay, if we have a 64 based processor, it means it can execute 8 of these processes at the same time. So in our instruction cycle, it will determine which kind of phases fall under these 2 main stages. So we said there's the fetch stage, and then there's the execute stage. So we say that under the fetch stage, 2 phases are executed, which is fetch, okay, from the RAM, decode, convert the data, since the data is binary. Remember the computer, there's binary and then there's also bytes, okay? So it needs to be able to convert from one form to the other when it's processing or sending it back to the RAM. And then as part of the execution stage, there's actually execute, where the CPU is actually doing the work, and then there's store, where it's sending it back to its original location, okay? And you can see in the diagram below that all of these happen at specific components, okay? The control unit is the one that's going to be doing the decoding. Okay, let's start with fetch. So fetch, where are we fetching from? We're fetching from RAM, the spreadsheet. It goes to the control unit, okay? It's going to decode everything and put it in the proper registers. Then we have the ALU, which executes the actual comparisons, calculations, and so forth, the functions. And then after that is finished, then the storage phase actually occurs, and the data is sent back to the RAM. So that's how a typical CPU actually executes an instruction.
Yeah.
Is there a question?
Yes, sir. Can I ask a question?
Yes, you can ask.
So I've heard about what do you call this? What registers are? Yeah, can you explain to me what they are, like a literal description, because like what they are in the computer? I know what a CPU is. It's a
Okay.
chip inserted inside the computer.
Okay, that's a good question. So we're still gonna cover the memory hierarchy, and I'll just put it out there because registers are actually part of the CPU. I don't know why they actually don't include them in the diagrams of the CPU. Most of the diagrams of the CPU on the internet, they don't include them there. But along with the control unit and the ALU, which is what you see in front of you now, the control unit, the ALU, and the registers, they all are housed within the actual CPU chip. So the registers are a form of storage. Okay, when the CPU fetches data from the RAM, okay, remember the RAM, you saw in the slides earlier on, it's these are two separate chips, components, and they're located in different parts of the motherboard. So when data or instructions is fetched from the RAM, the CPU must have an internal, like an office where everything is going to be stored. So the registers, you can look at them like the offices of the CPU. And this ALU executes everything from the registers. It's a form of internal storage. I hope that answers your question.
Watch.
Okay. So moving on to interrupts. So there needs to be a way for input-output devices to be able to communicate with the CPU. Okay, input-output devices, examples being our mouse and our keyboard. One way with which this is done is through interrupt requests. Okay, we tend to abbreviate it as IRQ, interrupt requests. So what is an interrupt? An interrupt refers to a special event that forces the central processing unit to terminate its normal program execution and carries out other tasks related to that event. The benefit of interrupt is that the CPU can execute other tasks while the input-output attached to the system can carry out other operations. This improves the CPU utilization. So what are we saying here? Why is it called an interrupt? Because when you move your mouse, it must take first priority. The CPU can't say I'm busy executing a program, something that's happening in the background that you can't even see. Input-output devices take first priority. Okay, so they disturb the CPU. The CPU literally has to stop, okay, and attend to them. Hence, we call it an interrupt. And this is like an electronic signal. Okay, you move your mouse, an electronic signal is sent to the CPU, and it attends to the mouse, and hence you see that the cursor moves immediately without delay, regardless of whatever the processor is doing. Okay, so whenever any external device wants to communicate with the RAM, it has to go to the CPU. The CPU is the boss. Everything has to go to the CPU. So interrupts mean a signal is sent to the CPU to say, stop, attend to me, I need something from the RAM. And then the CPU gives the mouse or the keyboard or whatever input device is there, it gives it access to those addresses or locations, okay? So that's what you must understand about these interrupts.
Sir?
Yes.
I thought the motherboard was the boss.
No, just because it has the term mother there, it doesn't mean it's the boss. The motherboard is, and I hate to put it this way, it's one of the less significant things out there in the computer. It's like if you look at the human body, the motherboard is like the skeleton. What is the skeleton without the heart and the brain? You understand? So we don't classify the motherboard as the basic element. Although all of these components, it's important to acknowledge that they have a role that they play. But when you talk about the architecture of a computer, the motherboard is just it's just a motherboard. That's just it. There's nothing more I can say about it. It contains ports. That's the only special thing about it. And obviously the address bus that we saw. So the CPU is the brain. It's the brain. It's central. That's why we say it's central processing unit, because it's central to everything. Everybody who wants to do something has to go through it. Before you can interact with the RAM, you have to go through me. That's what it says. Okay, so these interrupts can be classified into 4 main classes. We have interrupts that come in the form of a program. So a program is crashing, it's experiencing errors, it'll force the interrupt on the CPU. Okay, immediate response must be sent to the user. We have interrupts that is actually initiated by a timer. Okay, so every single time a system or a computer reaches a particular point in time, then it initiates an interrupt. We have input-output devices, okay, I/O input-output devices, our mouses and keyboards, which we mentioned, and also true hardware failure. So if a particular hardware is now failing, that will force an interrupt. If the RAM is failing, then it causes obviously an interrupt to the CPU, okay? And the computer would either not turn on or whatever. So moving on to our next concept now, which is direct memory access. So we spoke about interrupts. We say it's a form of communication. IRQ requests or interrupt requests are sent to the CPU asking for permission to use the RAM. Okay, but there are devices, some of them are more expensive, but there are devices that are fitted with DMA technology, which means if a device is fitted with DMA technology, it can bypass the CPU and go directly to the RAM to ask for memory locations. Okay, so we say direct memory access transfers the entire block of data directly to and from the memory without going through the processor. So processor is involved only at the beginning and the end of the transfer. Processor executes more slowly during the transfer when processor access to the bus is required. You can picture components like the GPU, the graphics card. The graphics card cannot wait, okay? In actual fact, some graphics card come built in with memory, but that's a debate for another day. So let's take video cards, graphics cards. They can't wait for the CPU. They can't ask for permission from the CPU. So they are fitted with DMA technology, and then they do not have to consult. Okay, they do not send an interrupt. They go directly to the RAM whenever they want to initiate a task. So we have IRQ request versus DMA request. DMA is new technology used in more modern and more expensive computer components. So also Monday, yes.
Could you please go back one slide? I just have a question about that. It says transfers the entire block of data directly to and from the memory. What is a block of data?
Remember that we send data. It's basically data is sent in bits. Okay, when they say block, there's nothing deep to it. It's just saying the entire 8 bits of data.
Oh, okay.
Yeah,
Thank
that's
you,
basically what. There's nothing tricky about it. It's just saying that it doesn't need to break it down to anything. It's just showing the importance of this technology, that it just sends everything at the same time without even consulting the CPU directly to the RAM. Okay, so then we also have the memory hierarchy. When it comes to a computer, what are the different forms of memory that we have? Well, somebody asked about the registers. We discussed the registers. So you can see the registers sit at the very top. They are one of the most smallest type of storage found in a computer, specifically within the CPU. Okay. We have our cache memory, which is L1, L2, L3. I'll save this for the slide that follows. We have our main memory, which is our RAM and so forth. You can see that on the right-hand side of this diagram, they actually have this minimum and maximum capacity that you normally find these components in. So we also have our main memory, and then we have our hard drives or our solid state drives. Okay, so as you move from the top to the bottom of the memory hierarchy, you'll notice that storage capacity grows. Okay? You notice that storage capacity grows. So now I want to shift the focus to these L1, L2, and L3, because I'm sure you may be curious what exactly that is. So,
Sir,
yes.
when they talk about cycles, like, is that what do they mean by cycles exactly? Could you please explain it?
An instruction cycle. So every single time a process is executed, a cycle is done. You remember that the different phases, and the stages of instruction execution. So if it happens once, that is one cycle. Okay? That is one cycle. Don't get confused. Don't look at the right-hand side of the diagram too much. Don't try to understand too much. The stuff that I touch on is the stuff that you really need to be or grasp your attention on first, okay? But to answer your question, the cycle speaks to how many instructions can be executed on that particular component or level of the hierarchy. Okay, so we saw the cycles: instruction, fetch, decode, execute, and store. That is one singular cycle. So how often, okay, how it relates to this is as we move from the top to the bottom of the memory hierarchy, it's all about accessibility. How often is a particular device accessible? So a hard drive stores all your data, okay? So it's accessed more regularly than how it would be on the registers in terms of storage, okay? So that's what it means, the number of cycles. You can see as we go from top to bottom, the number of cycles actually grows.
Okay.
Yeah, so L2, L1, L2, L3. What is cache memory? Okay, does anybody in the class know what a cache is or what a cache does, just in generic terms? You've never heard of this term cache before?
Well, it's something you store stuff in it.
You store stuff in it, yes. Okay, anybody else want to add to that?
It's volatile.
It's almost like RAM, so you know.
It's almost like
RAM temporarily stores data so that you can access that particular application faster. Let's say maybe on WhatsApp. Let's say maybe on WhatsApp, and you want to you don't want to keep on getting on WhatsApp, like starting all over. So you can just use the cache memory to go in where you are in WhatsApp, you know.
Okay.
That's cache memory.
Okay. So so cache memory in terms of computers, it's the exact concept that you guys defined. It's the ability to remember what you just recently done. And if you loading, let's say you're loading Facebook for the first time on your computer, what happens? It takes about a couple of, depending on your internet connection, okay? But you understand that it loads for some time. Then the next time you're on Facebook, just instantly everything appears. Why is that so? Because of the cache. Okay, so the cache is not unlimited. It's actually very small. Okay, so it may store the last, depending on the size of the CPU or the technology you're using, but maybe it may store the last 20 executed instructions, the most recent 20 executed instructions, and anything beyond that 20 would then need to go through that entire cycle, instruction execution cycle again. Okay, so cache memory, we say cache closer to the CPU that stores recently accessed data from the RAM, holds instructions to be executed next, and variables for the CPU. So a CPU normally has by default a level 1 catch, which is the smallest type of catch, but is also the fastest. So all of them, most modern CPUs by default has a level 1 catch. The level 1 catch is inside the CPU along with the registers, the ALU, and the control unit. Now, more modern computers would add an additional, catch, which now we call level 2 catch. However, with the level 2 catch, it sits outside the CPU. It's just between where you find the RAM, okay, and the CPU. It just sits somewhere between there. So it's an additional layer, but we can see how the reason why the level 2 catch was invented is to add additional capacity. But the level 1 catch, for the mere fact that it's inside the CPU, it's going to be faster than the level 2 catch. It's just that it's not going to be the same capacity. The reason why the level 1 catch is going to be faster is because the CPU doesn't have to go through the bus. You can see these lines, these arrows represent the bus. So for the fact that the CPU doesn't have to go through the bus to access the level 1 catch, it means it's going to be faster than the level 2 catch. Okay, so for other more advanced technologies, you're going to see they even add a level 3, an additional chip for the catch. Okay, so that's what you need to take into account. Catch stores, just like the registers, it's a small, tiny location of storage. It's there to store the recently executed task. Whenever, maybe the catch has slots for 20 only, and then when it's always adding to it, okay? It's always adding. It's like a ladder. It's always adding to it and deleting anything that it feels like it's outdated or old. Okay, so the benefits of it is instead of the CPU going to fetch, doing the whole fetch, decode, execute, and store cycle again, it just goes to the level 1 catch, finds anything there, doesn't, goes to level 2 catch, finds anything there, doesn't, then it goes to the RAM. But if it finds what it's looking for here as recently executed transactions or instructions, then it can continue to actually execute those instructions. Okay, so that's how significant cache memory is in computer or CPU.
Sir.
Yes.
Now, can I just add something I think I've learned?
Yeah,
this,
sure.
Something I can relate to, you know, so the word catch itself, you know, it catches data.
Yeah.
So it basically catches data to, you know, just store it for later use. So that's why check we teenagers, we also like, us men, we tell ourselves that we mustn't catch, you know, for a woman. I think I catch. So I think it's relatable to life, you know. Seriously.
Look, what I can say to you is whatever helps you remember the answer in the exam. That's all I can say. So if that's how it is, if they say don't catch feelings, but unlike you, the L1 and L2 and L3, they are programmed. Okay, they were invented to catch. You can still change yourself because you weren't invented to catch. But L1, L2, L3, they have to by default catch this data as it's moving between the RAM and the CPU. Okay.
Yes. Life lesson, don't be a CPU.
Don't be invented to catch. So the instruction register is just one of the types of registers that we have. There's different classes of registers as well. And the control unit is in charge of ensuring that this piece of data of this instructions goes to this type of register. So the instruction register is the most common one because it stores the instruction that we're currently executing. So the instruction that is currently being executed by the ALU is stored in the instruction register, okay? And in this slide that follows, they basically discuss the different classes of registers. So if we just we said the RAM stores what? Data, it stores programs, it stores instructions. Okay, so the registers themselves have to be divided to accommodate. It's like you attend multiple modules, and each module would have its own register to keep track of your attendance. So that's why there are different classes of these registers within the CPU, okay? And the control unit is in charge of ensuring that whatever is fetched from the RAM goes into the correct type of register. If we take the memory buffer register, this type of register basically stores the data that is coming from the RAM. We have the memory address register. This register stores the address that we must fetch next. Okay, what address must we fetch next? That is stored within the memory address register. Then we have the instruction register, which is storing the 8-bit of block of code that is currently being executed, currently by the ALU. Then we have the instruction buffer register, which is storing the queue of instructions that still need to be executed by the ALU. Then we have the program counter, which stores all the different programs that have been executed, and the reason why they call it a counter is that it increments. Okay, so if it's a 32-bit processor, okay, we're assuming that it's 8 bits per program, so it's going to count by 4. So it's going to take the first 4 programs, then the next 4, and then the next 4. Okay, so that's why you have the program counter register. And then we have the accumulator and multiplier quotient. So this just stores the output, the result. Once the result is generated, then it goes to, and it's still awaiting to go back to the RAM, and it's going to go to the accumulator and multi-quotient register. Okay, so these are the different classes of registers that exist. Okay, so in conclusion, in this lecture, we actually have an overview of a computer system, and we covered instruction execution, we covered processor and memory, processor input-output request, we covered interrupt and interrupt processing, we covered the memory hierarchy, we covered cache and cache memory principles. We also covered multi-core versus multi-processor concept, and we also covered DMA, direct memory access. Okay, so you can see how technical this module is, but fortunately for you, since you're going to be writing it on an online exam, I think you are on the safe side. Okay, so it takes time. You need to, the only way system software you grasp its computer architecture is by forming patterns. And I like some of you brought up things that you can relate to in the real world. That's definitely one way, if you're still starting off, relate some of these concepts to the real world. Myself, when I was conducting the class, I tend to make a comparison of the computer and the human body. So that's one way at which computer architecture can be understood. Formulate patterns between everything that we mentioned today. Sit down and think about how it happens in sequence. Okay, so now I can say that we concluded Unit 1. Are there any other questions before we conclude the session for today?
Sir?